Hello, everyone. Today we are in lecture 5 of our course Survey of Optimization, offered by the Department of Postgraduate Studies of the Institute of Cybernetics of the National Academy of Sciences of Ukraine. So today we are in the 5th lecture. Just wait a minute. I will. Refer to this. Now for okay, here we are. Okay. So as I said, we are continuing our topics regarding mathematical programming. And today we are going on with lecture 5 on LP assumptions and the graphical method for LP problems, the graphical method of solving LP models. So the course developer is Butenko Sergey, professor of NDM University in Texas, and the course advisor is Doctor of Science, Stasiuk Petr Ivanovich, Institute of Cybernetics. And the course instructor is I, Valaviki Lenin. Today we will concentrate on the following points. They are major methods of solving LP. Then we will consider production planning problem formulation, then practical implications of using LP models. Also, we will solve the known problem Heavenly Punch Incorporated using graphical approach. Also, we will solve graphical advertising campaign planning problem. And we will introduce classification of LPs based on the problems introduced today. Now, to begin with, let's list major problems of major methods of solving LPs. The first one and the easiest one is the graphical methods, which is applicable for two variables. Then the substitution method, the linear combination method, simplex method, Hachiyan's algorithm, the ellipsoid methods introduced by Noam Shor, Karmakar's algorithm, which refers to an interior point method. Today, we will introduce the graphical approach method actually for solving two variable linear models, linear programming models. So, now first, let's talk about the LP formulation in general form, and we discuss the implicit assumptions made by any LP model. So for this purpose, we will look at the following working examples. So this is a production planning problem. We assume that we have a production manufacturing facility that produces n product denoted as P sub 1, P sub n up to n, which uses n different resources, types of resources such as raw materials, labor, and so on and so forth. These resources are denoted by R sub 1 up to R sub m. Also, we know that each unit of product P sub j requires A sub ij resources from R sub I, and it is known that each unit of product P sub j will sell for C sub j dot. So we know actually the same practice. We also have the constraints of resources. So we assume that the resources are already there. In other words, we already purchased them before. This is what we call the sunk cost. We already paid for the resources and now we need to use them in the most efficient possible way. So the amount of resources available would be B sub I, units for resource R sub I, and this is for I between 1 and m. Now, producing one product P sub j requires this A sub ij units of resources. Yeah, so and we need to decide how many units of each product we want to produce so that we could maximize its weekly profit or revenue. No, it doesn't really matter in this case. So, okay, no, this is a very typical situation. And in fact, many examples that we considered so far fall within this general framework. So we know very well how to formulate this type of problems. We use index I for the resources and J for the product. And then our decision variables would be x sub j, which reflect the number of units of product J to manufacture, where J varies from 1 to n. Then the adaptive function is easy to formulate. Specifically, our objective is to maximize actual weekly profit. And the profit we get from the product J is given by C sub J times X sub J, and then we sum up all the contributions of each product to the profit to obtain the total. And of course, we are maximizing, so our objective is to maximize the summation of S sub J's and X sub J's over J from 1 to n. So this is actually the final presentation of the formulation of the objective function. Now, at step 3, we specify the constraints. Then the resource constraints just express the fact that the quantity of each resource R sub I is limited, and the limit is given by B sub I. To express the total amount of the resources I that we use, we need to look at how much of the resources I each product J takes. That is given by their coefficients A sub J, A sub 1, A sub 2, and so on and so forth, F sub J. And by these coefficients, therefore, if we produce X sub J units of product J, the total amount of resource I used for the product J is given by A sub ij times xj. Yeah, so this is actually spelled out expression of this. And again, we need to sum this over all the products produced between 1 and n in order to get the total amount of the resource I used to produce all of the n products. So this total cannot exceed the upper bound on the resource denoted by B sub I, and always done for every I between 1 and m. So this is the line standing for the resource constraint. And finally, we have the non-negativity constraint for all the variables, decision variables, as we cannot produce a negative quantity of a product. So in summary, we obtain the following formulation. We maximize the profit. We maximize the profit by the summation of the revenue obtained from the individual products. Then subject to the M resource constraints. Here we are. And then we also have the non-negativity of the decision variable. So this is a very standard LP formulation. We can write it out in an expanded form as it is shown on the slide. So this is actually all the summations are spelled out clear. All of these can be written in a much more compact format if we use the matrix representation for our data. In fact, all the coefficients from the objective here, from the objective function can be put in a single vector. Then all the right-hand sides of the resource constraints can be put in right-hand sides of the resource constraints can be put in another vector. So the vector for Cj's will be of length n, and B sub I would be of length m. Yeah, then we can put all the coefficients that we have on the left-hand side of the constraints into a single matrix with m rows and n columns. So before we do that, let's formally discuss what a vector and a matrix are. A real n-dimensional vector is an ordered set of n real numbers x sub 1, x sub 2, x sub n, and is usually written in the form. So we use the single notation for the vector. Very often it is a capital letter, by the way. So for the components of the vector, we use square brackets and put them as a column inside those brackets, provided that this vector belongs to the n-dimensional Euclidean space. So this format refers to the column vector, so because it is specified vertically. So the same we can actually put as a row vector, which is actually presented here. By default, for clarity, unless it is specified otherwise, by a vector we will mean the column vector. Then we can transpose this column vector in order to obtain a row vector. Then another representation of the vector is this one. Yeah, then instead of listing explicitly, we actually can use compact form and denote the number of components within this vector by introducing the index and actually the limits of this index from 1 to n. So this is another notation of a vector. So the number x sub 1, x sub 2, x sub n again are called the components of x, of the vector x. Now about a matrix. A real matrix is a rectangular array of real numbers composed of rows and columns. So usually we say that we have an n times n matrix. This means that there are m rows and n columns in this array. Normally, always actually, rows go first. So we already mentioned the transpose of a vector. No, and here actually we have again the notations for the variables with two indices. The first index will stand for the row number. The second index will stand for the column number. So in an expanded, in a spelled out way, again we put every value in the brackets in a rectangular array, and all this belongs to the set of real numbers with the dimension m times n. For a matrix of m rows and n columns, and we say that the matrix A is of order m times n. Actually, normally we use capital letter actually to denote matrix. Now, in a more general case of a matrix, if you want to transpose a matrix, we essentially write all the rows as of the original matrix as columns of a new matrix, and the other way around. So essentially, we swap rows and columns if we need to transpose a matrix, and this way we obtain actually the transpose one. So if our original matrix was m by n, so then the transposed one is going to be n by n. And it is denoted using a capital letter T as an upper index. So it is denoted this way. So now we are ready to put our general LP formulation in a matrix form. So recall that we were discussing this generic production planning problem, and we had the objective of maximizing the summations of C sub j, x sub j products for j between 1 and m, and we had m resources. We had m resources constraints, which were spelled out before. So the spelled out way of this, I will recall it, okay, is presented on this slide. And of course, we had the non-negativity constraints. We had the non-negativity constraints of the number of products produced, so meaning actually for all their decision variables. So no, for the coefficients of the objective, we'll represent them in the vector C, with the components C sub 1 up to C sub n. And remember that we agreed that on default, our vectors are column vectors. So therefore, since we wrote it in a row here, we put it in a row. Here, we put it in a row. We use the transpose symbol actually for this vector in the objective function. X denotes the vector of variables x sub 1, x sub 2, x sub n. Initially, it is already transposed, so therefore, we don't need to repeat actually this symbol here. So therefore, the objective function looks like C transposed times x, where C and x are vectors. Similarly, the vector B will be the vector of the right-hand side. So you'll have B sub 1, B sub 2, B sub m, and so on. So this vector is of length m. And we explicitly write it as a column vector, so we don't need to put the transpose symbol because it initially was a column vector. So then the vector of variables x, actually we have discussed it already, and finally we put all the coefficients used in the right-hand side of the constraints into an m times n matrix. So you see here we have n rows, n columns, so we'll put all of these coefficients in a matrix denoted A capital, which is given by A sub 1, 1, A sub 1, n, F sub m1, A sub mn, actually the final. So this matrix is quite interesting. Normally, we call this a technological matrix. Technological matrix because essentially this matrix and these coefficients here describe the technology by which you would produce the products, all the requirements of the resources, and so on and so forth. So therefore, the final view in the compactive fashion will look like C transpose times x to maximize for the objective function, subject to matrix A times vector x is less than or equal to vector B, and x stands for the non-negativity of the decision variable. So another specified view of the column or of the vectors and matrices are represented here. So the left-hand side of these constraints, if you want to put them in a matrix, that is nothing else but the product of A and the vector x. So therefore, actually, recall how to multiply matrices and vectors, because here we deal with a scalar multiplication. So another form of, like when we substitute these values, so another form of the module formulation will look like as the summation of the products by the number of the summation of the cost of the products and product units summed up by the number of products and subject to the resource constraint. So where x sub j is a non-negative value. By now, we have considered many different linear programming models arising in different situations. And we have seen that we can solve some small-scale cases easily in the solver. But in fact, software based on the state-of-the-art algorithm for LP is very scalable and can handle problems with millions of variables and constraints. And this scalability of the state-of-the-art algorithms for LP is what makes it one of the most attractive optimization-based tools in the real world. So the relative simplicity of these models, also the scalability of algorithm, and therefore implementability in software packages represent the main advantages of LP. However, as any technology, no matter how powerful linear programming, has its disadvantages. So, no, in fact, the simplicity of LP models, which we stated as an advantage, happens to be also the main disadvantage of LP, because in many cases, linear models are overly simplistic, and the linearity assumption is very restrictive, and most of the real world process is non-linear by nature. Therefore, the question arises how adequate the LP models are in describing these real-life processes. Let's discuss in more detail the implicit assumptions that come from using the linear models. Two of them come out of the definition of the linear functions as it, and also the properties which are involved into this definition. We'll first recall that a linear function is a relationship of the independent variable x from the n-dimensional Euclidean actual space, and which is given by the sum of the products of the constant real coefficients and the variables involved into this function. Then this function actually possesses such property as additivity and proportionality properties. The additivity property stands that the function of the sum of the variables is equal to the sum of the functions of these variables for any real x and y. And also the proportionality property stands that if a variable is multiplied by any real number, then the function of the x with this real number is equal to this real number multiplied by the function of x. So these are just standard, some of the standard properties of the linear function, which we need actually for our linear programming assumptions. So therefore, let us see how these properties affect an LP model and in which other assumptions are relevant for linear programming. So the implicit assumptions that we make in any LP model are listed on the slide. The first two of these assumptions are essentially a definition of a linear function as it. Now, to illustrate them, let's consider a simple example, simple linear actual function, 7x sub 1 plus 3 times x sub 2. Now, obviously, these there are two variables here. They are linear, as we see, because they are to the first power. So therefore, actually, this example is relevant. So as for their proportionality, proportionality assumption says that contribution of a variable is proportional to its value. So of course, this is the case for linear functions because the way the variable is included in the function is with the coefficient 7 for x of 1 and coefficient 3 for x of 2. In our example, the contribution of each variable toward the function value is proportional to the corresponding x of 1 value. So let's say x of 1 is 1. Then the contribution to the function will be 7 times 1, which is 7. Then let's say x of 1 is 2. Then the contribution to the function, overall function, will be 7 times 2, which is 14, and so on and so forth. So it's proportional to the value of x of 1, of the variable 6. Similarly, the contribution of the variable x sub 2 is proportional to the value of the function, which is given by 3 times x sub 2. So it is. So this property actually works. Then additivity assumption is a part of the definition of the linear function contributions, and stands that contributions of variables are independent. Okay. When I increase or decrease the value of x sub 1, it only impacts the corresponding term, but it doesn't impact the other term. So therefore, these terms are independent of each other. Then again, this is a part of linearity assumption because everything is linear in linear programs, and we cannot avoid both of these assumptions. So the third assumption refers to the divisibility assumption, and it states that decision variables can take fractional values. So this essentially says that we cannot require variables to be integer. So fractional values satisfying all their constraints will be considered feasible solutions to our linear program. Some of the examples we have considered before dealt with production of items whose quantities must be integer. In this case, of course, we cannot insist that the linear model is precise. In fact, it allows the fraction values for the items where it is physically impossible. For example, when we speak about cars or carriers, reversible or non-reversible carriers. Yeah, so for the items which are countable. However, even in cases where we are dealing with inherently linear programs, their linear approximations can provide some useful information about the system that the model describes. So in the last assumption, finally, the last assumption of linear programming listed here is the certainty assumption, saying that each parameter is known with certainty, but it is well established that there are too few things in our life and in the real world that are certain. Well, but for us to stay within the framework of the linear programming, we have to take this assumption as a must. So these, because the coefficients, what's certain actually, the coefficients are known ahead, the number of variables is known ahead, they're not randomly selected. So therefore, actually, there is a high degree of certainty in such mode. So these four assumptions are always implicitly present in any linear programming model, and we have to recognize that whenever we use a linear programming model, you cannot really get rid of any of these assumptions. So they are an integral part of this methodological framework. Of course, if you look back at our examples, at all the examples, and which we have considered so far, and I strongly recommend you to do so, to go back and analyze every single LP model we formulated so far, and think how reasonable these assumptions are for that model. So if you do this, you will notice that in most cases, at least one of these assumptions does not make much sense. Then we may argue why we should even think about using this methodology if the underlying assumptions may not be true. But the same argument can actually be made about any methodological framework because nothing is ideal and perfect. The real-world systems tend to be very difficult to describe precisely, and typically we have to resort some kind of an approximation, and we have to balance between our ability to describe the model with a good level of approximation and our ability to solve the corresponding problem. So let's say if we drop some of these assumptions, well, then the model will get extremely challenging, meaning we cannot really solve them to optimality. So for example, if we drop the first two assumptions, so these two that would allow the functions of the model to be, which allow that they are linear, but if we drop them, so it means that it will allow for them to be non-linear, then we fall into the realm of non-linear optimization, which is extremely difficult. If we drop divisibility assumption, Then we are talking about integer programming models, and these are also extremely difficult to solve. And finally, if we drop the certainty assumption, then we talk about stochastic optimization, which is again a class of problems which are extremely difficult to solve. So linear programming is a methodological framework that can be claimed to be wrong in most cases, but in a very large number of cases, it is extremely useful. And that is why it is a very popular framework used in pretty much every industry these days. So let's consider the problem which we introduced in the second lecture, and we have been working on this problem since the beginning of the course. But this time we will solve it graphically. I will skip the text and rather I will explain it using the formulated model, originally formulated model. So what we have here, there are two variables involved, x of 1, x of 2. So they are our decision variables. If there are two variables, so it means that we can plot the feasible region of such LP. So another way, we can actually find a graphical solution, because graphical solution is good for two variable models. So our working example is the heavenly couch problem that we formulated before. In this model, we are looking at manufacturing two types of areas. Here they are, areas, non-reversible and reversible. So we manufacture x of 1 units of non-reversible and x of 2 units of reversible. So we make $15 per unit on producing non-reversible pairs and $25 of profit per unit for reversible ones. Also, we have some resource constraints. Here they are. The resources we are using to manufacture these products are the solid fabric, solid color fabric, and previous fabric that is used for the reversible area. And then we also have the manufacturing budget constraint. It is no more than $2,000. So we also the manufacturing process, and we have a limited amount of money to spend on manufacturing costs. Finally, we have a demand constraint that tells us that no more than 350 units of non-reversible carriers can be sold. And we have traditionally non-negativity constraints for the decision variables, of course. So how do we solve this graph? What we need to do is to plot all the constraints on the plane. Because there are only two variables, it is easy to do. And this is what we will do. We start plotting with plotting the lines for every constraint. Let's see how we do it. So for this one, for the constraint for solid fabric constraint, we plot a line x of 1 plus x of 2 equals 450. Here's the table. Then we refer to the inequality relationship, and we see that we need to select the, this line splits the plane into two halves. So our task is which half to select. So as the relationship here indicates to the points which are no more than 450, so this relationship refers to the points below this line. So that's why the feasible region for this equality for this constraint is the one shaded here. As their condition of equality is involved into this relationship, so the line with this line, the bounded lines, will be included into the feasibility region 2. Then, for the printed fabric constraint, this is the line corresponding to the equation x of 2 equals 300. Again, we have less than or equal relationship in this inequality, so meaning that for the feasible regions, we select the lower actually half of the plane. And again, as we have the equality condition involved, so the line will be included into the feasibility region. For the next constraint, budget constraint, again, we plot the line 4x of 1 plus 5x of 2 equals 2,000. Again, according to the inequality relationship indicated here, we need to select the points below this line, and again, the line is included into the feasible region. So this is what we have for the demand constraint. This is x of 1 equals 150. So therefore, the points which are lower than this line will lie to the left of this line. And the non-negativity constraints will refer to the upper right quadrant of the plane. Next step for us is to find the points which are feasible with respect to all the constraints. So for this, we need to find the overlap of all the shaded regions, and the set of points that satisfy all of these constraints will be the feasible points. So therefore, the set of points in the overlap are here. So they're shaded. So, and they give us the feasible set for our LP. So let's see what it looks like. So this is the overlap, as we see. We can see all the 4 constraints, including their non-negativity of the variables. And here it is just presented in a better resolution. So we can find the points of intersection of different lines here. For example, the budget constraint and the solid fabric constraint. So here they are intersected. Here, now this is actually we do in a standard algebraic way. We just turn them into the lines and to make them equal, and then actually using the substitution or maybe some other tools, actually we can find the point of intersection here. We can find the intersection point here and here. So these points are called corner points. So, and they are extremely important. So why the corner points are important? Because we will soon see these are the points where we should look for the optimal solution. Speaking of which, how should we determine the point that is optimal? Yeah, or maybe there are more than one actually. More than one actually optimal points. So obviously we need to look at the objective function first, and for this, this is just a feasible region, but we also need to pay attention to the objective, what we want to achieve. So the objective function was 15 times x of 1 and 25 times x of 2. So let's plot the objective function for a particular value of the objective which we want to select. Now let's start with the realistic assumption, like arbitrary, yeah, so some arbitrary level of profit that we want to achieve. Realistic level of profit, let's say $3,000. Then, by setting the x of 1 variable to 0 and x of 2 variable to 0, so we find the points of intersection with the x1 axis and x of 2 axis. So 2 points actually determine only one line, on the single line, and we can draw a line here, and we will denote it as a blue dashed line. Here it is. So, and what this type of line is referred to as isoprofit line. Why it is isoprofit? Because the value of the profit in every point of this line, including these 2 points, is the same. It is 3,000. Iso stands for the same in Greek. So in our case, this line corresponds to the same level of profit. Again, it was 3,000. In case of minimization problem, we would call it here we maximize. Yeah, remember that we need to maximize. But if it were minimization, so in our case it is isoprofit line, then we would refer to isocost line. because normally what we minimize is the cost. So we see that this ISO profit line at the level of $3,000 gives us a lot of feasible points. Yeah. So actually, what we're interested in, we definitely we do not care about these extensions. So we need actually only the segment which falls into the feasible region. But as we see, there are infinitely many solutions to these problems. And in every point of this segment, so the profit will be 3,000. Now let's raise the value and shift up our target to 6,000. Yeah, so actually we double the profit. So if we double the profit, then these values will be doubled too. So and we receive these lines. So therefore we actually move the line in the gradient direction. And then what is important here is that these two lines are parallel because they have the same coefficients at the variable. And we get another blue dashed line. Again, it has a segment falling into the feasible region, and which produces an infinite number of optimal solutions, at least not optimal, feasible solution. So, well, let's move it again. So we move. So here's another, and here we move. Till we stay in the feasible region. So we have to stay within the feasible region. Say we actually, and the highest point where the ISO profit line actually falls into the feasible region, still being parallel to the previous ones, is this one. Is this one. Yeah, so you see that all these ISO lines are parallel. Then eventually we reach this point here, denoted as x sub 0, after which we are not going to have any more overlap with the feasible region. Oh, definitely, but let's move just a little bit higher, and immediately there is no intersection with the feasible region. So therefore, actually, what this is the extreme point after which we cannot really move. So this x asterisk is the optimal point, the optimal solution. And now we just need to find the coordinates for x asterisk. And we see that this point lies on the intersection of the printed fabric constraint and the budget constraint. Here we are. So therefore, we write them as a system of equations. So here, instead of less than or equal, we actually can use equations. And after solving the system, you find that the intersection point is 125, 300. By plugging in the solution into their objective function denoted as this asterisk, we find that the optimal profit level is 9,375. Please note that these values coincide with the solution presented by their software when we solved this problem using AMPL, both directly and using their AMPL executable and using the NEOS platform. We solved our original heavenly pouch problem. Let's see what happens if we slightly modify the problem by raising the price by $5. We see here, actually, I changed the color. Instead of $15, generating $15, we actually have $20 generated actually for profit. Assume that the demand and other conditions remain the same. all the constraints actually remain the same. So only the coefficient of x sub 1 in the objective function actually has increased. So if this stays the same, it means that the feasible region remains the same. It doesn't change. So what will change will be just the slope of the isopropyl line. Another thing which I want to point your attention to is that what the coefficients here and here are proportional. So therefore, if I multiply with this inequality by 5, I receive exactly the same coefficients as in the objective function, meaning that what the objective function will be parallel to the budget constraint function. So now let's again refer to the feasibility region. Yeah. So we have some feasible regions the same as we expected. So it is the same. Yes, it is the same fact. The slope of the iso function is different. It is here. Still, let's move it in the direction of the gradient. And we see, as I explained before, that it is parallel to this constraint, the budget. So we move, and eventually we fall into the segment between x0 and x sub prime. Here, this is actually the optimal solution that we had before, though there is another solution actually which appeared here, and not only this solution, but also all the values in the segment which connects these 2 points. So we obtain infinitely many solutions. Note that both of their values are corner points corresponding to the same level of the objective. Therefore, both of them will be the optimal solution as well as the points between them. By looking at these illustrations, it becomes apparent that no matter which objective function you have, when we try to move this isopropyl line, you will always hit one over their corner points. But even if it were this way, yeah, you would hit this point. Or, I don't know, this way already, yeah, or this way, yeah, again, you hit this point, yeah. So therefore, the corner points are always included into the optimal solution. On the slope change, okay. Then another thing which is important, once I have 2 optimal solutions, I have infinitely many, because all the points lying on the segment between these 2 points actually will be optimal solutions too. So infinitely many, we can, it is, first of all, it is clear from the plot, and also actually we can also prove it rigorously algebraically. Moreover, you see the word optima. The letter A stands for the plural of the word optimum. If it were the integer program where you have the integrality constraints, then you would have a situation when you have exactly 2 optimal solutions, but not for linear program where as soon as you have 2, everything in between the ones will also be optimal. Let's consider a minimization problem. A retail store is planning an advertising campaign aiming to increase the number of customers visiting its physical location as well as its online store. The store manager would like to advertise through a local magazine and through an online social network. She estimates that each $1,000 invested in magazine ads will attract 100 new customers to the store, as well as 500 new website visitors. In addition, each $1,000 invested in online advertising will attract 50 new local store customers, as well as 1,000 new website visitors. Her target for this campaign is to bring at least 500 new guests to the physical store and at least 5,000 new visitors to the online store. So our task is to formulate an LP to help the store minimize the cost of its advertising campaign and solve it graphically. Well, traditionally, we start with identifying decision variables. As we have clearly have two types of advertising, so therefore we will set the variables accordingly. We can define the decision variable for this problem based on the decision options that we have here. So essentially, we need to decide how much money we are going to invest in the magazine ads and to online ads, actually counted in thousands of dollars. Please remember that the units of measurement is thousands of dollars. So we have two decision variables, x sub 1 and x sub 2. Based on this, we can formulate the LP as follows: minimize the sum of x sub 1 plus x sub 2, actually investment to every type of ad, subject to. If we look at the store visitors that the advertising campaign attracts, every $1,000 invested in the magazine advertising brings, here's the contribution, 100 new customers. So this is the coefficient at x sub 1 to the store. And every 1,000 invested into on online advertising brings 50 new customers to the store. So this is the coefficient x sub 2. Similarly, we actually determine the coefficients for the constraints for website visitors constraints. And of course, non-negativity constraint for the decision variable. So here are three constraints. So we formulated an LP model, and it was easy to do, of course. So now going back to the implicit assumptions of LP and trying to analyze each of them. How much they are reasonable. Now, we may say that perhaps this model is not extremely realistic. So, these linearity assumptions in this case might not be extremely good because you invest $1,000 and the first $1,000 you invest may attract 100 visitors. But the next actually $1,000 invested may bring some diminution actually, so fewer number of customers. So the linearity assumption is quite a bit of stretch in this case. Nevertheless, as we are talking about strategic decision, this model may be somewhat useful to try to determine a reasonable advertising strategy. So we have the constraints, so we can plot the feasible region that which might get to the optimal solution. So here is the region. So we have one constraint, store visitors constraint, and website visitors constraint. And of course, all this plane will refer to the non-negativity of the decision variable. So the overlap is represented by the shaded area here. Let's look at that. We see two lines. The points are feasible with respect to the lines and to the non-negativity constraint. So the feasible points are in the intersection of the half planes contained above these two lines, as well as to the right of x-axis. So this shaded feasible region is infinitely large, so it stretches up to the positive infinity. So it is not bounded on the top. Though realistically, we would also need to have some upper boundary of the budget, because remember that we are talking about the budget, because essentially this model can assume the possibility of the infinite budget, saying that you would spend as large of the money as you want on advertising campaign. Perhaps you may go to the infinity if you are infinitely wealthy, or you spend someone else's money, not your own, which might happen, but it is not very realistic. Anyway, the points that are far away in that direction towards the infinity here are not of interest to our model to start with, because we are trying to minimize the budget here. So we are minimization. So we are in the either cost line for minimization. So we do not care about the upper bound, because we need to minimize our expenses on this advertising campaign. So we start with a ballpark figure of $15,000. Now remember that actually everything is counted in thousands of dollars. So that's why I just put it. No, and here actually we scratch a line, either cost line here, dashed line, and we see that the whole line lies in the feasibility region. So if we invest $15,000, it means that we can easily reach our goals. So we can see that there are plenty of feasible solutions with the budget value of 15,000. So we try to see if we can reduce the budget and still reach our objective. So this leads to another either cost line of $10,000, which is still what the whole line is in the feasible region. Again, it produces an infinite number of solutions. So, and there is some more space, so we move it down, 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 down as much as we stay in the feasibility region. And while moving in this direction, we reach the point over the asterisk, which is the corner point here, in the intersection of the two constraint lines. If we move further, we start moving even further here, more, then we immediately drop outside of the feasibility region. So meaning that if we invest less than this point actually into the advertising campaign, we will not reach our objectives in terms of attracting new customers. So therefore, you cannot go below this budget right here that corresponds to the point over 20/3. And giving them evenly split and giving the values of 10 divided by 3 for every type of advertising. So what this example shows here is that even though the feasible region is infinitely large, we can still find the optimal solution to our problem. And the infinitely large region does not mean that we will not have an optimal solution. However, if we were maximizing with this model, say everything is the same, but I change my objective from minimization to maximization, the fact that I have an infinite feasible region allows the possibility of having an infinite objective right here. So we see that if we were maximizing, then our objective would be to spend as much as possible, which would not be a smart objective, but just shows the point you could have an infinitely high solution. And we can use this example right here. What it means in practice. Typically, it means that our objective is infinitely large when we are maximizing, meaning that our model is not very good. It's either unreasonable or unrealistic. So therefore, for example, in this case, you would want to to waste as much money as possible, which doesn't make any sense. So, but again, theoretically, it is possible to have an infinite solution. Usually, if instead of minimization, we would do maximization and are going to positive infinity. So this means that you have an unbounded problem. For the problem to be unbounded, you have to have an unbounded feasible region so that you could go to the infinity, that you had space to go towards the infinitive objective. But the other way around, if you have, say, an unbounded feasible region, but it doesn't mean that the problem would be unbounded if we are in the minimization case. You can still have a finite optimal solution, and it is presented here. And we will call, on convention, we will call the problem unbounded only when there is no finite optimal solution, and you can go either to negative infinity for minimization or positive infinity for maximization. Another example is if, let's say, I had a limit of $5,000. $5,000. Yeah. And what we see, and I want to minimize my budget. At the same time, I do not want to spend more than 5,000. Yeah, so the contradictory objectives. Then, and I add this constraint into their model. And what we see that this line, none of the points of this line fall into the feasibility region. So clearly we will not have any intersections of these points with the feasible region if we include this constraint into the regional law, meaning that we will not have any feasible points at all. In this case, we say that the problem is infeasible, and we cannot find a solution that would satisfy all of the constraints at once. Again, when you have an infeasible LP, it means that either you are being unrealistic with your model or something is wrong with the way you formulate it. In this case, you're being unrealistic when we speak about the budgeting of 5,000. You are trying to achieve unrealistic goals in terms of bringing the customers with the budget of $5,000, which is just simply impossible. Even with these, and here actually next slide shows the solution, how we found the values of 3,333 and their objective of expenditure objective of 6,066. So the interpretation of the results is such that the store should spend $6,666 on advertising and split this budget evenly between the magazine and online advertising. So even with these very easy examples, we have seen enough to classify the LPs in terms of the type that we can have and the type of situation that we can encounter when we solve the general linear problem. So we have seen that the LPs can be either feasible or infeasible. When we try to solve our LP and see that it is infeasible, then our conclusion is that the problem we try to solve is unrealistic and something needs to be changed about it if you want to have a feasible solution. If LP is feasible, then what can happen to it is that in some cases we have the optimal solution. And we say that LP has at least one optimal solution, and we call it an optimal LP. This is one type which we have for feasible LPs, and actually this is what we had with the original heavenly pouch problem. And we also seen in the example that where we were trying to maximize the budget of advertising campaign instead of minimizing it. We saw that the problem can be unbounded because you could allocate infinite amount of money to the advertising campaign, and you would be just wasting money. Yeah, though if this is your objective, you may go to the unbounded LP. With optimal LP, we also saw that there is a possibility that you have a unique optimal solution or infinitely many optimal solutions. The situation when one of the ISO lines was parallel to the body constraint. So we cannot just with the linear programming program, with the linear programming model, we cannot have just two optimal solutions. Once you have two, you will have an infinite number of optimals. So this decision tree illustrates different types of LPs in terms of their solutions. Again, recall there to be used as we have the letter A, the ending A here. It represents the plural of the word optimum. Optimum is a singular. Okay, so here we are. Thank you very, very much. We are all finished.